Exercise 1933 is similar to exercise 1930, but here instead of putting 2 branches on the ring, we're putting 3. So it says starting with benzene, so we're just going to use pure benzene, and using any other reagents of your choice. So those will be those reagents we learned for this chapter that we're going to focus on. Design a synthesis for each of the following compounds. In some cases, there may be more than one plausible answer. So we're trying to make this from benzene, starting with benzene. And the first step is just to think about what recipes you need to use in order to add these different groups on individually. And then after you know which recipes you need to use, you can think about the order that you would add them in. So this group here on the right, you notice that you have a new carbon-to-carbon bond, so instantly you should be thinking Friedel-Crafts. And you have this carbonyl group there. And so that is a sign that you have Friedel-Crafts acylation. That would be on the far right over here. So we want to keep the acyl group, so we don't have to reduce it. We can just do this top part. And in general, to put an acyl group onto a benzene ring, you would have that same group. So if you ever are unsure about what the carbon chain is, put a box around the carbon chain, and then redraw that. But instead of a bond going to benzene, have a bond going to chlorine. So that's your acyl group. And then you just need the metal catalyst, so AlCl3. So that's how we can put that branch on there. The bromine, that's bromination. We can put that on with Br2 and either AlBr3 or FeBr3. And then the branch on the left, that's another alkyl branch, right? This is a carbon-to-carbon bond, so again we're thinking Friedel-Crafts. Now, this one doesn't have the acyl group, it doesn't have the carbonyl, and so you might be able to do this with Friedel-Crafts alkylation, which would be nice, it's a little easier. So if you did do that, you have to worry about carbocation rearrangements. Now, to draw the carbon chain that you need to add, just draw whatever's in that box. Instead of a bond going to benzene, have a bond going to chlorine. Ultimately, in that mechanism, the chlorine comes off, and the carbon it was attached to becomes a carbocation. And anytime you do Friedel-Crafts alkylation, you have to worry about whether the carbocation can rearrange. So this is a secondary carbocation. That carbon's bonded to 2 other carbons. And so it is more stable than anywhere else in the molecule. At one of the ends, those are just primary carbons. They're only bonded to 1 carbon. And so a secondary carbocation is more stable than a primary carbocation. The more carbons a carbocation is bonded to, the more stable it is, because it can borrow electrons from those carbons to help stabilize itself. So that's the most stable carbocation we can find, so that carbocation is not going to rearrange, and we can use Friedel-Crafts alkylation. So we have our alkyl halide, and then the metal catalyst, AlCl3. So those are our recipes. But now we have to think about the order that we want them in. So we have these 2 groups that are ortho to each other. And then this third group is either para to the alkyl group or meta to the bromine. Okay, now if you think about the directing effects of each of these, the bromine is ortho-para, and the alkyl group is ortho-para, and this acyl group is meta. It's a moderate deactivator. So there are several orders we can put this on, and it would be completely correct, or acceptable at least. Ultimately, we'd probably get a mess. So there are maybe more efficient ways. Some ways are more efficient than others for putting this on. But we could put this on in several ways. So if you're ever in doubt, if you ever feel confused, just try something and see if it would give you your products, even if it would give you a whole bunch of other stuff. And if it would, then that's an acceptable answer, and if it wouldn't, then try the same reagents in a different order. So here, we could put, for example, we could put the bromine on first. And once you have the bromine on the molecule, once you have the bromine on the molecule, that's an ortho-para director. So whatever you put on second is going to add to both the ortho position and the para position. Now we don't really want anything on the para position of the bromine, but we do want this, we do want that alkyl group at the ortho position. So we can add our alkyl halide in the metal catalyst. And we'll end up getting two products. We will get the ortho product, which is what we want, and we'll end up getting the para product. We'll probably actually even get a slight majority of the para product, because there's less steric hindrance for the isopropyl group there. But we'll get both of these. We can always separate them using chromatography. So we do get at least some of the product we want. Now, if we add this third group, we have to think about which group is going to be doing the directing effects. The bromine is weakly deactivating, and the alkyl group is weakly activating. So it's the alkyl group that's going to be doing the directing effects. It's more activating. So this is an ortho-para director. It'll either direct the incoming group to the ortho positions or to the para position. Now one of the ortho positions is taken, and so our incoming group can't go where the bromine is, but it can go at either of the other two positions. So we have our acyl halide, the metal catalyst, and we'll end up getting two products here. One where we have the acyl group ortho, and then one where we have that acyl group para to the isopropyl group. And actually the major product there would be the one that has the acyl group para, because there's less steric hindrance, there's less crowding at the para position than at the ortho position there. So we do end up with that synthesis, we end up with the molecule that we wanted. And we get a whole bunch of other stuff. So it is kind of a mess, but it's a possible synthesis. All right, let's try that same process with B. So here's our little recipe book. So first, let's think about what recipes we need to use, and then we'll think about the order that we need to do them in. So at the top left here, we have that NH2. We know we can put in a nitrogen on the ring by doing nitration. But that leaves us with an NO2. We want NH2, so we can just reduce that with iron or zinc and HCl. So this one is first nitric acid and sulfuric acid, second iron or zinc and HCl. So that's how we can get that done. Next, we want to think about the bromine. Well, we can add bromine with Br2, and either AlCl3 or Fe, or I'm sorry, AlBr3 or FeBr3. Either one works. Okay. Finally, we have this alkyl group. We can see a new carbon-to-carbon bond, so we're definitely thinking about Friedel-Crafts. Let's see if we can do Friedel-Crafts alkylation. In that case, put a box around that alkyl group, redraw it, but instead of a bond to benzene, have a bond to a halogen. Now, in the mechanism for Friedel-Crafts alkylation, at first you try to make this an awesome electrophile with a full positive charge, and the full positive charge forms wherever you had the halogen. So we'd have it right here. But notice that carbocation is a primary carbocation. The carbon is only bonded to one other carbon. Right next door, if it moved, it would be a secondary carbocation, because it would be bonded to two carbons. And that's a more stable carbocation, because the positive charge can borrow electrons from more carbons. And so you'd get a rearrangement there. And that branch would not add as a propyl group, it would add as an isopropyl group. So you would have, if you did Friedel-Crafts alkylation, you would end up getting this branch, not the one that they have here. So we can't do Friedel-Crafts alkylation because it would give there would be carbocation rearrangement, and it would give us an isopropyl group instead of this regular propyl group. So to avoid carbocation rearrangement, we'll do Friedel-Crafts acylation. That's the workaround. When you use this acyl group, the positive charge that forms on the carbonyl carbon is stabilized through resonance in what's called an acylium ion. And since we don't want the carbonyl, we can just reduce it afterwards using that mercury zinc amalgam with HCl and heat. So first step, we'll redraw that same branch. Instead of the branch to benzene, we'll have it to chlorine, and then we just add the acyl group. So this is going to be our first step, that in the presence of a metal catalyst. And our second step is to reduce that acyl group, change those bonds to oxygen to bonds to hydrogen. And you'll do that if you have that mercury zinc amalgam with HCl and heat. Oops. So those are our recipes, but now we need to think about how to add them on. Well, this branch here is ortho to the bromine and para to this other NH2 group. The NH2 and the bromine are meta to each other. So if you think about the directing effects, this is an ortho-para director, the bromine is an ortho-para director, and the NH2 is an ortho-para director. So really, we can put this on in a number of ways. The only way we can't put it on is with this NH2 first. If we have that NH2 go on first, then it's true, we could get the alkyl group adding para. It'll also add ortho, but we could get it adding para. But then this alkyl group is only weakly activating. This is strongly activating. And so that would control the directing effects, and you wouldn't be able to add the bromine meta. So we can't add that first. But we can definitely add it last. And either of these are both ortho-para directors, so it doesn't really matter which of those we add first. Either way, when they're both on, the bromine is weakly deactivating, the alkyl group is weakly activating, so the alkyl group will control the directing effects, and so you'll be able to add this third group on para to the alkyl group. So let's start with our benzene. And again, if you can't see everything when you're first trying to do it, just try putting one branch on at a time. We only have a few different recipes to work with here. Just try putting a branch on and consider the directing effects of the branch and see if you can, and what's the strongest activator, and so what's controlling the directing effects. And see if you can work one step at a time instead of thinking globally about the whole problem. So let's say we put the bromine on first. So now that bromine is an ortho-para-director. That means that whatever we put on next would add to one of the ortho positions, and it'll also add to the para position. So I'm going to put on this ortho branch here, because we won't be able to put this. The NH2 group is meta. So I'm going to put on the other branch, the alkyl branch. And the first step is just adding the acyl group along with the metal catalyst. So that would put that on the molecule. Now we do have two branches here, but notice the most activating group still is the bromine. Bromine is here weakly deactivating, and this is moderately deactivating. So we still can't add the other branch because the directing effects are controlled by the bromine, which is an ortho-para director, and this needs to add meta to the bromine. So we'll do the reduction. That will give us that. And now we have two groups. We have the bromine, which is weakly deactivating. We have the alkyl group, which is a weak activator. So the alkyl group is the more activating thing, so that controls the directing effects. And that is an ortho-para director. So we'll get the product ortho and para. And I should have written here at this step, I drew the ortho product, you'll also get the para product there. So that creates something of a mess, but it's good to include that. Oops. So you get both of those products, but we can use the top one. So we can separate them and then continue with the reaction. So now we have that alkyl group, that's the strongest activator, it's an ortho-para director, and if we can add our third group, this is going to be in two steps. First, we'll add nitric acid and sulfuric acid. And that actually gives us two products. One where the NO2 adds ortho, and one where it adds para. So the ortho product is kind of a mess, but we can use this para product. Notice the NO2 is strongly deactivating, the bromine is weakly deactivating, and the alkyl group is weakly activating. So the effects are still being determined by the alkyl group. But you can reduce that NO2 using iron or zinc. Iron or zinc and HCl. And that would give us the product we want. So that there is what they wanted us to make. And so this synthesis would be a valid synthesis from making that molecule. It makes a whole bunch of other stuff too. There are some side reactions, because when you use ortho-para directors, you don't just get one product, you get two. But we're able to make the product that we want. Okay, let's try C. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . So the first step is just to think about what recipes we want to use to put each of these branches on. To put a chlorine on, we'll use Cl2 and AlCl3. And that's true for this other chlorine. To put the NH2 on, as we've seen, we do it in 2 steps. You first add an NO2 with nitric acid and sulfuric acid, and then you do iron and zinc with HCl to reduce that. And lastly, we have a new carbon-to-carbon bond here, so we're thinking Friedel-Crafts. It would be nice if we could do a Friedel-Crafts alkylation, because that would just be 1 step. And so if you're ever worried about what R group you add, just redraw the branch, and instead of the benzene, add a chlorine. Now, if you ever do a Friedel-Crafts alkylation, you have to worry about carbocation rearrangements. When you're turning this into an awesome electrophile that the benzene would react with, take the chlorine off. Imagine the carbocation there. And that's a tertiary carbocation. That carbon is bonded to 1, 2, 3 other carbons, so that's really stable. Any other position on the molecule, any one of the carbons next door, those are all primary. Each of those are only bonded to 1 other carbon. And so that carbocation would not rearrange, so we can do the Friedel-Crafts alkylation. So those are the recipes we're going to use. These are the recipes we're going to use. Now we just have to think about the order to use them in. Well, the chlorines and the tert-butyl group are meta to each other. And that seems a little awkward because chlorine is ortho-para-directing. This other chlorine is ortho-para-directing. And this is ortho-para-directing. So those you'll only be able to put that on. You won't be able to put those on with just each other. The directing effects for those conflict because the chlorines and the alkyl group are all meta to each other, but they're all ortho-para-directors. So everything kind of boils down to this NH2. This is a strong activator. You have the lone pair there on that benzylic position. It's a strong activator, and so it's an ortho-para-director. So it'll push things to go in the ortho positions and also in the para positions. And that's exactly where we want our branches. So that's the first thing we want to put on, because the directing effects will put our branches where we want them to go. So we'll take pure benzene. We will nitrate it. Then we'll reduce it, so those bonds to oxygen turn into bonds to hydrogen. And so now we have this strong activator that is also an ortho-para-director. So now you can do this in several ways, but I think the most efficient way is to add the tert-butyl group first, to do the Friedel-Crafts alkylation. So because if you add that tert-butyl group is famous for being really bulky. It's really crowded. So it'll almost entirely add to the para position, because the ortho positions are so crowded. You might get a small percentage of the ortho product, but it's going to be a really small percentage. So almost all of your product will be the para product, which is the product we want. And then if you treat that with the Cl2 and AlCl3, and you could just use excess, the only place for those to go is at the ortho positions, because the para position is already taken up. Now notice that because we have a strong activator, once we put that tert-butyl group on there, that's an alkyl group, that's only a weak activator. So the directing effects are still controlled by the NH2. And that's why the branches we add on after will add ortho or para to the NH2. But of course we also already have that tert-butyl group on the para position, so they'll only add ortho to the NH2, the most activating branch on the ring. So that is a valid synthesis for this. Okay, last one for these. So first let's just think about what recipes we need to use, and then we'll think about the order that we need to do them in. So for the bromine, you can add a couple things, but you definitely need Br2, and you could either use FeBr3 or AlBr3, either way. For the chlorine, Cl2 and AlCl3. Technically, you could also use FeCl3. For SO3H sulfonation, you would use fuming sulfuric acid. That's water with sulfur trioxide bubbles going through it. And the sulfur trioxide reacts with the water to create the sulfuric acid. So those are our three recipes that we need to use. Now let's think about the order we need to do them in. Remember that the SO3H looks like this. So you have those pi bonds to electronegative atoms on the benzylic position, which makes this a moderate deactivator and a meta director. The chlorine and the bromine are both weak deactivators, and they're both orthopara directors. So the most activating things are the chlorine and the bromine. So once we have those on the ring, they will control the directing effects. So if we need anything added meta, we would have to add that meta director first. So that's one way you can do this, and actually I personally think that's one of the more efficient ways. If you take this benzene ring and you treat it with fuming sulfuric acid, sulfur trioxide gas bubbling through water, then you put the SO3H onto the ring. Now that's a meta director, and it's the only thing on the ring. So whatever we put on next is going to add meta. We want the chlorine to be meta to that SO3H. So we use the recipe for the chlorine. And we get the chlorine only on the meta position. Well, now the chlorine is the most activating thing. Right, the SO3H, that's a moderate deactivator. The chlorine is a weak deactivator, so the chlorine is more activating, and so the directing effects will be controlled by the chlorine. The chlorine is an orthopara director. So you could either have the next branch added ortho or para. Now technically, you'll get a mixture of all three of these. But notice how big the SO3H group is. It really hinders stuff from adding right next to it. That area is really crowded. And so the para position, one of the ortho positions, will be disfavored, and by far the major product you would get here would be the product you want, the bromine adding ortho. The bromine adding ortho away from the SO3H group. Now it's true you'd also get a very small amount. You get a very small amount of the other ortho product and also of the para product, but you can see bromine is a really big atom. It's bigger than chlorine, and chlorine is the size of a methyl group. It's really big, and the SO3H group is really big. You can see how there's going to be a lot of repulsion between those, and that disfavors those products. So by far you get the product where the bromine has plenty of space, and the SO3 group has plenty of space, or at least more space than they have in the other reagents. And so this is a pretty good synthesis. So the general procedure for these is to identify what recipes you need to use to put each branch on the ring. And then think about the order. And when you're thinking about the order, if you ever get stuck, don't worry if you can't see the whole synthesis. Just try doing it one step at a time. Try adding something. And then consider the directing effects of that thing. Add the second thing. Look at what's most activating, and consider the directing effects of that most activating thing. If you can make the product, even if it's messy, I will accept it as a valid answer. So that's the procedure for making these polysubstituted benzene rings.